Welcome to the lecture on Coulomb's law and dipolar self-energy. What we're going to find is that a discussion of the electrostatic attraction that occurs between two oppositely or similarly charged particles that we know about from the second semester of physics, or second quarter of physics on the West Coast, will manifest itself a few more times in the class. So many of the forces that we're going to be talking about might be electrostatic in nature, but also have some entropic or also some quantum mechanical phenomena that underpin them. But first we need to know something about Coulomb's law. This will be a little bit of a review at first, but we're only going to spend a few minutes on the basics. So this is chapter 3. Coulomb forces, or charge interactions. And what do I mean? Well, suppose we have charges Q1 and Q2 that are separated by distance r. Now, these are drawn quite far apart, but remember, we're still talking about r as the distance between the centers of these charges. Even if they're ions and they actually have quite large electron clouds, we're talking about the nucleus to nucleus, the internuclear distance. Okay, so if we have Q1 and Q2, Q1 produces an electric field, and the electric field times the charge of Q2 produces a force on Q2. Now, depending on the sign of the charge, it can be either repulsive or attractive. So far, so good. We have an electric field due to Q1, which we will call E1, which is Q1 over 4 pi epsilon naught r squared. I'm going to reverse the epsilon naught and the epsilon because of the way they are in my notes, because I don't want to be inconsistent. And this has units of volts per meter. Epsilon naught is the permittivity of free space. I was asked yesterday what words I look forward to saying in class. One of them is flocculate. The other one is permittivity. That will be on the exam. And it has a value of 8.85 times 10 to the minus 12 Coulomb squared per Newton per meter squared. Epsilon is the relative permittivity. It's also one of the most fun words to write in all capital letters. Or the dielectric constant. And air, so epsilon of air is approximately epsilon of a vacuum, or 1. What is the dielectric constant? The dielectric constant of a medium reflects its ability to be polarized in an electric field and to screen charges. We'll talk a lot more about how molecular structure of a particular solvent medium gives you a specific value. Well, it's hard to calculate a specific value of dielectric constant, but we'll talk about why one material, one medium might have a higher or lower dielectric constant than another. So to give you a preview, it has to do with its electronic polarizability. So how easy is it to deflect the electron cloud about the nucleus in an electric field? It has to do with the strength of any permanent dipole moment that can be oriented in an electric field. And it also has to do with any reinforcing mechanisms within the dielectric medium, for example, hydrogen bonding. If the polarized state can be reinforced in some way by a very strong dipole or hydrogen bonding, then it tends to have a higher dielectric constant as well. I don't know what day tonight is. Okay. The electric field produces a force. The electric field due to Q1 produces a force on Q2. Force on Q2 due to Q1. Q due to Q. The force equals the charge on 2 times the electric field, or Q1 Q2 over 4 pi epsilon naught epsilon r squared. And force has units of newtons. Okay. That's the electric field, the force. How do we get the energy? The energy of this interaction. So the potential energy of an interaction is the work done against the force to bring Q1 and Q2 together in some proximity r, to some internuclear distance r. So we'll do the integration. So it would be free. The free energy, which is going to give us the same thing as the potential function. Of the Coulomb interaction. W of r, I'm going to start over here so I can use the whole thing. W of r starting at infinite distance to r, so this is the work done to bring Q1 and Q2 together from infinity. So infinity to r of minus f of r dr. So we have minus equals minus the integral from infinity to r of Q1 times Q2 over 4 pi epsilon naught epsilon r squared equals plus Q1 Q2 over 4 pi epsilon naught epsilon times r evaluated from infinity to r. And the final result is going to be W of r equals Q1 Q2 over 4 pi epsilon naught epsilon r, or to write this another way, z1, z2 times E squared, which is the fundamental charge squared over 4 pi epsilon naught epsilon r. This has units of joules, and E is the fundamental charge. Which is the charge of an electron or a proton, which of course have opposite signs, of 1.6 times 10 to the minus 19 coulombs. Z1 and Z2 are the valencies. That is, Na plus would be 1, Cl minus would be minus 1, and so on. Okay. Suppose you have a single atomic species or ionic species in a vacuum. And think about the potential energy. So we usually think about potential energies as only really having value only really having a physical meaning when there are interactions happening, when you could either increase or decrease potential energy. But think about this. There's a neutral atom, and then there's an ion. Say you add or subtract an electron from the neutral atom. Which has greater potential energy? Neutral or charged in a vacuum? The charged does. But it's just free to float around. There's no force on it. It's just a charged thing in a vacuum. There's no electric field, no other molecules atoms or ions for it to interact with. How do we think about the concept of potential energy of a standalone ion in a vacuum? Now, you can think about it, suppose potential energy can be thought of as discomfort at a buffet, where you have an infinite amount of food in front of you, effectively, and as you eat a little bit more of the things that you would never prepare for yourself at home because it's too unhealthy, you just eat more of the mac and cheese, and as you eat more and more and more, you become more uncomfortable, and your potential energy goes up. The exact same thing happens with ions. That is called the Born energy of an ion. Or the self-energy of an ion. Or just the electrostatic self-energy. So what we're going to have, suppose we have some sphere with radius A, And we're going to calculate the work to charge the sphere from 0 to big Q in increments of dq. We're going to ignore the fact that protons and electrons have this thing called the fundamental charge. We're going to pretend that we can break up the fundamental charge into an infinite number of infinitesimally small dq's, just like bites of mac and cheese at the buffet. It turns out that the big Q, the big Q is actually not quite so small. The fundamental charge is not quite so small. It actually represents a significant amount of electrostatic discomfort. So dW equals Q dq. This is the work from the little bit of charge that's already there, plus the next little infinitesimal charge that's being added, over 4 pi epsilon naught epsilon A. And we will call this mu I, the self-energy of the ion, which is the integral of dW from 0 to big Q of Q dq over 4 pi epsilon naught epsilon A, or Q squared over 8 pi epsilon naught epsilon A, or using our convention from that board, ZE quantity squared over 8 pi epsilon naught epsilon times A. Notice how we have the square, which eliminates any negatives. So this is always positive. So the self-energy of an ion is always positive, regardless of what charge it is. Why is it always positive? Well, by convention, if you take stuff from an infinite distance, which has 0 potential, and you bring them to some distance, in this case confining them to the same sphere with radius a, then you have some positive interaction. So positive is in some sense unfavorable. Of course, you don't know if what the physical manifestation is going to be until you have another particle nearby with which it can interact. But the baseline potential energy of just this ion is going to be positive. So mu I of an ion is greater than 0 because confining dq's is unfavorable. Incidentally, suppose you have a sodium atom, or you have a sodium nucleus with its appropriate number of electrons. In a vacuum, what is its ionization state? What's its most favorable ionization state? Be confident. Even if you're wrong, it's okay. +1? Anyone disagree with +1 in a vacuum? Going once, going twice. 0. Someone said 0. If there's nothing there to ionize it, the most favorable state is going to be 0. So these might be some intuitions that you have, and the purpose of this course is to disabuse you of those intuitions. In a vacuum, the most favorable state by the Born self-energy of a sodium ion is going to be an ionization state of 0 in a vacuum, because nothing is there to ionize it. There's no water to ionize it. There's no chlorine atom to ionize it. So it's going to be sodium 0 floating in space. How about chlorine? Most favorable state for chlorine is also 0. Now, in the presence of any kind of reducing agent, like sodium 0, it's going to take on a negative charge, and that's going to be its most favorable state because it fulfills the octet rule, and you get all that great stuff from chemistry. So interestingly, if you have a sodium ion, or sodium atom, and a chlorine atom, all my life teaching and learning chemistry, I never know whether to use a script L or a straight line L. Anyway, these are my struggles. I won't burden you with them. At an appropriately large distance, the sodium and the chlorine atoms interact or not interact. Say 10 nanometers, 20 nanometers. A large distance by atomic scale, but not a large distance for nano engineers. Say 20 nanometers. Do they interact? Yes, how? They interact by the electric field. We have a name for this. Uncharged things interact. Dispersion force. Yes. So they interact by the London dispersion force over some appropriately large distance on the order of several nanometers. Now, if you bring them close together, so this attractive force is van der Waals. But if you bring them close enough together, what's going to happen? The electron's going to move from where to where? Sodium to chlorine. And then you'll have a Coulombic attraction. So it's almost like this is the marlin and this is the old man in the sea. And you get close enough and you harpoon the marlin with the electron, and then the attraction becomes much stronger by Coulombic effects. It's actually called the harpoon effect. So plus or minus an electron, you get sodium plus Cl minus, and now you have a Coulomb interaction, and this is called the harpoon effect. Yeah. Still in a vacuum. Now, if you took these atoms and you separated them and separated them and separated them, theory predicts that the electron would actually go back to the sodium atom at the correct distance. I don't know if it's ever been shown experimentally, but theory predicts. Okay, that's all I'm going to cover from Chapter 3. Chapter 4 is combining charges into a dipole, not combining, but bringing them into a physically tethered position, tethered by covalent bonds of a molecule, where one side is some partial charge and the other side is another partial charge. And what we actually have in that case is two self-energies there's a self-energy of each side of the dipole. So we the harpoon effect itself is not an ionic bond, but once the harpoon effect occurs, you have an ionic bond. So you really have two Born energies in a dipole. You have the Born energy of the positive side. You have a Born energy of the negative side, which is going to be unfavorable. But then you have a favorable term for bringing the two charges together. It's almost like a consolation prize. Like the two sides of the dipole are full of potential energy and self-hate for eating all of that mac and cheese. But then when you bring the two together that have opposite signs, the potential energy goes down. Okay, this is chapter 4. Polar molecules. And they could have the polarity. A dipole in a molecule can arise from differences in electronegativity. So differences in formal charge. Differences in electronegativity. And also asymmetry. What do I mean by asymmetry? You could have a molecule where there wasn't much of a difference in electronegativity between the atoms, but they're arranged in an asymmetric way that produces a very small dipole. Let me give you an example. Suppose we have this organic structure, and suppose we have a CH3 group that's coming out of the board at us. If we don't care what direction it's going, we draw a straight line. But suppose we're specifying this is coming out of the board at us. Every molecule in the flask of this type of molecules has the same exact configuration. That little bit of asymmetry is enough to give you a dipole. It's not a very strong dipole at all. I would never call that a polar molecule or a polar solvent in a process, but nonetheless, there is a very tiny dipole. Okay, so these are the sort of the three ways in which you can get a dipole. 1 and 2 are predominantly what we're going to be talking about in this class, but you should know that number 3 can exist. So what are some examples? HCl, H2O, or something more complicated like CH3 taken twice, CO, which is acetone, or as the Italians say, acetone. And the dipole moment orientation follows, just to make it confusing, the opposite convention of the electric field vector. Where we have our partial positive charge and our partial negative charge arranged thusly, and the dipole moment U. This is Y, because the U and the Cl look the same. This is the dipole moment vector. Why? So that it aligns parallel to an electric field. So electric field, just so you remember, looks like this. So potential energy is minimized when a dipole is parallel to the electric field. Potential energy is minimized when U is parallel to E. Yeah. Okay, sorry. Forget this. Forget the fact that this thing in a bubble is in the same chalkboard as this. This is in an in an externally applied electric field, say where this side of the board was the positive terminal, or positive side of a capacitor, and this side was the negative part of a capacitor, the electric field would be pointed this way. And the dipole would align parallel to the electric field vector in order to minimize its potential energy. This is not the electric field produced by the dipole. Good question. We can calculate the dipole moment U simply by multiplying Q times L, where Q are the partial charges and L is the distance between plus and minus Q. And just to give you an example of some of these strengths, for partial charges plus or minus the fundamental charge, and L equals 0.1 nanometers or 1 angstrom, then the dipole moment U will have the value 1.6 times 10 to the minus 29 Coulomb meters, or 4.8 D, where D stands for debye. 1 debye equals 3.3 times 10 to the minus 30 Coulomb meters. One wonders why they even decided to make that up there a chalkboard. Okay, so molecules can have dipole moments, but bonds can also have dipole moments. Dipole moment in units of D. N-alkanes, so hexane, octane, anything with a straight line of carbon atoms with hydrogen atoms sticking off of them. Dipole moment of 0. How about something that has differences in electronegativity but also has symmetry, like carbon dioxide also has a dipole moment of 0? How about SO2, 0 or not 0? There's it's a little trick. It's bent, right, because it has, because if you do the Lewis dot structure, it has lone pairs, which force the oxygen atoms down. So it actually does have a dipole moment. 1.62. Water, 1.85. Not a very strong dipole for a molecule that we consider as being quite, as having a lot of manifestations of being a polar molecule, like hydrogen bonding, like a high dielectric constant, and so on. Its dipole moment is not very large. The reason is because L isn't very big. Because, again, water looks kind of like a Mickey Mouse head with very small ears. CH3OH is methanol, byproduct of moonshine production. That's 1.7. Acetone, which the Italians call acetone, is 2.9. Sodium chloride, where we really start to get strong Q effects, where we have no longer sharing of the bonds but complete ionization, 8.5, and cesium chloride, where we have a similar situation in partial charges but a larger L because cesium is much bigger. We have 10.4. We can also have bond moments where we take all of the electronegativities and we do some trigonometry and we calculate what way the dipole moment vector is going to go. Then we calculate its magnitude. And we can look these up in a table, but here are some examples. A CH bond by itself is worth 0.4 dBi. An OH bond by itself is worth 1.51. Or we can also have group moments. It's a group moment. Like COH or COOH, where whatever on this side can be anything. Whatever is sticking off of the carbon atom could be anything. And these group moments, we have 1.65 and 1.7. So if we calculate what direction all these bonds are going and we resolve them along an axis, we can calculate the dipole moment magnitude and direction. We're not going to focus on this really in this class because it's kind of something that you did in second semester or second quarter physics. But let me just give you the example of water and we'll move on. Someone before me really liked blue chalk and really liked erasing with the wrong side of the eraser. One moment. Didn't help me at all. Okay. If the example is water, we have OH, and we have a bond moment for U of OH this way, and we have U of OH this way, and we know that the dipole moment vector, the total dipole moment vector goes this way. And this bond is something like 104.5 degrees. Then U of H2O is 2 times U OH times cosine of 1/2 theta, or 2 times 1.51 dBi times cosine of 52.25 degrees, or 1.85 dBi, which is what I wrote up there. Okay, similar to ions, dipoles also have self-energy. And since we already calculated the self-energy of ions and the self-energy that is the electrostatic potential energy of two charges approaching, we can just write down the dipolar self-energy. So the dipolar self-energy is the self-energy of the charges minus the energy to bring them together. So picture two ions of radius A where R equals L equals 2A. So you're just taking two ions, you're going to approximate them as spheres, and they're just going to stick together with only their outsides touching. They're not going to have a covalent radius, which is where the two atoms get closer than 2 times their radii. These are just going to stop as if they were hard spheres. This is much like sodium chloride would be. Okay, so here we have mu I for a dipole is all of this constant nonsense, 1 over 4 pi epsilon naught epsilon times q squared over 2a plus q squared over 2a minus q squared over r. These are the self-energies of the individual charges on either side of the dipole, the partial charges on either side of the dipole, and this is the gain or the lowering of the self-energy by bringing the two unlike charges together. Is that okay? So it's really like the Born energy here, and then the Coulomb self-energy here at a specified distance of the length L of the dipole. we can simplify this in two different ways. Q squared over 8 pi epsilon naught epsilon times A. Or we can also write this using a substitution that I'll show in a second of U squared over 4 pi epsilon naught epsilon times L cubed, where we've used the substitution of Q equals U over L and A equals L over 2. Now there's a nice problem in the notes, which is also in the book, the exact same problem of using the self-energy of an ion to calculate its solubility. And it's quite actually easy to do that. If you take an ion and you can calculate the way that an ion partitions between two different solvents with two different values of epsilon, the dielectric constant. I encourage you to do this in the book. All the solutions totally written out. Now that works really well for ions, but it doesn't really work that well for the dipole self-energy, except in cases where you have ideal dipoles, where ideal dipole is not really a thing. Don't write that down. An ideal dipole where the charges are, say, plus or minus the fundamental charge and have very small L's. So there are some limitations. And why did I give all those caveats? Limitations to the dipole self-energy. One, keep in mind that the dipole moment U does not uniquely define a charge distribution, because you can have a different U and a different L, but you can get the same U. Different Q's, different L's, different charges, different lengths, separations between the charges can give you the same dipole moment. But the dipole moment might suggest that they have the same properties, but they don't, because you can have small charges separated by a big distance might give you the same dipole moment as big charges separated by a small distance, because U equals Q times L. Okay. So U doesn't uniquely define charge distribution. The dipole moment can vary between solvents. You could have solvents that ionize, solvents that don't ionize. You could have solvents with different polarizabilities that partially change the partial charges. In principle, I don't know any examples of that, but certainly we know examples where ionization can change based on solvent. Like water, you might have amines become protonated, or acid groups become deprotonated in water. And molecules have other or additional self-energy terms. Like you might have a self-energy due to electrostatic energy. You might also have a van der Waals self-energy term if you're talking about molecules. Okay, let's talk about interactions between dipoles and charges and dipoles and other dipoles, which by the end of, in 20 minutes or so, by the end of class, we're going to get to the first of the van der Waals forces, which is the Keesom or the Keesom or dipole-dipole interaction. So picture an ion dipole interaction. Sodium plus interacting with water. Now you could think about this as using the following geometry. A interacting with charges B and C, where A has the charge Q is equal to EZ. In the case of sodium, it's just plus E. And C has the charge plus little q, and B has the charge minus little q, and the dipole moment vector is this way. Again, U equals Q times L. And the distance R will be the distance between A and the center of the dipole. Where this is a right triangle, and this is a right triangle, and this is 1/2 L, and this over here is 1/2 L. So the line segment BC is 1 L. This angle is theta, and this angle is theta. So what you're doing is you're summing the interaction potentials over the line segments of the line segment, along the line segment AC plus the line segment AB. So W of R is going to be minus big Q times little q over 4 pi epsilon naught epsilon times the quantity 1 over AB minus 1 over AC. We're going to use an assumption that's going to be valid for most reasonable distances in nanochemical and biological systems, which is called the point dipole approximation, which says that the distance between the ion or dipole interacting with a dipole is going to be smaller than the distance, than the length of the dipole. And that's going to be valid for all intents and purposes in this class. We never have to do out the whole trigonometry. Yep. This is minus QQ. Thank you. So the point dipole approximation, and the derivation is in the notes, but I'm not going to cover it here. It just says that R is much greater than L. It doesn't actually have to be that much greater, could be like 2 times or 3 times, and it still works out pretty good, pretty well. So with the point dipole approximation, what this boils down to is W of R equals minus QU over 4 pi epsilon naught epsilon R squared over, or minus, missing something important here, times minus Q times U times cosine theta over 4 pi epsilon naught epsilon R squared. Or if we write this out for Q, we get minus the quantity ZE times U cosine theta over 4 pi epsilon naught epsilon R squared. And from the beginning of class, actually this is the same thing as U times the electric field times cosine theta. In this case, maximum attraction, convince yourself that this is true, maximum attraction occurs with the dipole moment vector parallel to the electric field vector. Is there a question? Maximum attraction occurs in this scenario when theta equals 0 degrees with respect to the E field, and the max repulsion occurs when theta equals 180 degrees. What are some values of the ion dipole interaction? In the case of sodium plus and water, sodium has Z equals 1 and A equals 0.095 nanometers. H2O has A equals 0.14 nanometers, and U equals 1.85 dpi. So in the perfectly aligned case where W of R theta equals 0 equals 1.6 times 10 to the minus 19 joules, or 39 kT, or 96 kilojoules per mole. Is that a lot of kTs? That's somebody in here. Is that a lot of kTs? It's kind of a lot of kTs. 10 is a good amount of kTs. 10 is like the water-water interaction. We know water has a fairly strong potential because it's a condensed phase at, room temperature. You can also think about this as the energy required to orient polar molecules around an ion. The energy required to orient polar molecules around an ion. So we have solvation spheres, which are sometimes called, or solvation shells, or hydration shells in the case of water, where if you drop a sodium ion into water, the water molecules will orient the oxygen atoms toward the sodium, and it will coordinate these ions transiently, or coordinate the water molecules transiently. So the water molecules will stick in, but they'll swim away because 39 kT is pretty good, but there's going to be some distribution where there's going to be enough thermal energy in the system to break some of these bonds because there's going to be a distribution, and those molecules can exchange with others. In some cases, like really powerful ions or really highly charged ions, like aluminum 3+, for example, can coordinate water molecules, and they don't leave for like an hour. So it could be like nanoseconds all the way up to hours. So in Chapter 4, please read about hydration shells. There's a good aside in there. But I really want to focus on intermolecular interactions. Yeah. Correct. Yes. Yes. Yeah. How about dipole? Dipole-dipole interactions. And in the first case, we're going to consider that these dipole-dipole interactions are fixed. So we have two fixed dipoles separated by distance r. And we have theta 1 and theta 2, but this dipole can also move about the intermolecular axis with angle phi. This is dipole U1, this is dipole U2. And now we have a potential function that is a function of r, theta 1, theta 2, phi. And we won't do the tedious derivation, but it's minus u1 times u2 over 4 pi epsilon naught epsilon times r cubed times 2 times cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2 cosine phi. And we can simplify this if dipoles are in line. That is to say 1, 2, and so on. So if they're arranged in a line, we have W of r 0, 0, phi equals minus 2 u1 u2 over 4 pi epsilon naught epsilon r cubed. or in parallel or anti-parallel. Where we have one dipole this way, one dipole this way. W of R 90, 90 of 90 of 90 of 180 equals minus U 1 U2 over 4 pi epsilon naught epsilon R cubed. This is a stronger interaction when you have them in a line, but in some cases you'll have long dipoles that prefer to orient kind of log stacked, where it's sort of like sleeping in a tent with a bunch of people all at once that need to fit in, and you sleep head to toe next to each other. I don't know, maybe that's like a survival skill or something. So you sleep anti-parallel, and that's the most efficient way to pack long molecules next to each other. So even though this is stronger, this might occur in some cases. You just have to know what the geometry is. We're not going to spend a lot of time talking about fixed dipoles, but it is important, particularly in enzyme substrate interactions, for example, where you have fixed dipoles due to enzymes and substrates that serve to lock a substrate in place. So if U1 equals U2 equals 1D, then W of R theta 1, theta 2, phi equals 1 kT at R equals 0.36 nanometers in line. Or R equals 0.29 nanometers in parallel. Which again is really anti-parallel. So this is a fairly weak interaction, but it can align molecules with a fairly significant dipole. Yep. Because phi doesn't really have any degrees of freedom if they're both in line. Most it can do is like twist around an axis. Does that make sense? Yes, that's the case for both. Why did I write it?
So it's defined in the in-parallel as 180, but in the dipole it's just variable.
Can you ask me after? I need to get through this last thing. Okay, when you have dipoles in line, it's fairly easy just to use a static case in which you can just calculate the Coulombic interaction along specific line segments. But if you have dipoles in a real system where you have some thermal energy, they're not going to be fixed, right? There's nothing that says that these dipoles orienting in space can't move around sort of at freely. But are they going to move around with any orientation? No, the orientation is going to depend on the electric field produced by the other dipole. So you're going to run into a scenario where maybe far enough apart they're spinning around like this, but then as they get closer, some orientations become more favored than others, to the point where if you get really close, they are really kind of aligned because there's more electrostatic favorability to having these dipoles in line. And this is the, for this derivation, we needed the concept of angle-averaged dipoles. The derivation is in the book. I'm just going to skip to the end. Trust me, we don't want to do the derivation. Angle-averaged potentials. At large R, T, or dielectric constant, the dipoles rotate freely. However, some orientations are more favored than others. We're going to save 30 minutes by referring to page 84 and 85 with the caveat that you don't have to know it for any exam. And we get an ion dipole. These are angle averaged. Not fixed. These are the angle averaged potentials. Ion dipole will be W of R equals minus Q squared U squared over 6 times the quantity 4 pi epsilon naught epsilon squared KT, and the KT comes from the angle averaging because we have a Boltzmann distribution of angles, and that's where the KTs live, in the Boltzmann world. The KTs get imported through this angle averaging argument. R to the 4th, and then we have the world famous dipole angle averaged, and this is what we care about in terms of van der Waals forces, because it's the first of the van der Waals forces, is minus U1 squared U2 squared over 3 times the quantity 4 pi epsilon naught epsilon squared times KT R to the 6th. What are some important things to notice here? This is the first of 3 van der Waals interactions, and it follows an inverse R to the 6th dependence, and also it's the only one to be temperature dependent. Why is it temperature dependent? Because if you raise the temperature and you raise the amount of thermal energy available, then you allow these molecules to spin more and more indiscriminately, even if they're closer. So if you have a really high temperature, the Keesom interaction actually starts to go away. Whereas on Thursday's class and then Tuesday next week, we'll talk about the dipole-induced dipole or Debye interaction and the dispersion interaction, which are not dependent on temperature, because the angle averaging is dependent on temperature. So maybe if it's like this at a low temperature, maybe they go back to like this at high temperature. They can no longer interact, and the strength of this potential goes down. All right. Thank you very much, and see you next time.